This is the Pilot's Handbook of Aeronautical Knowledge, Chapter 3, page 3-9, high pressure below. Just did low pressure above. Now high pressure below. A certain amount of lift is generated by pressure conditions underneath the airfoil. Because of the manner in which air flows underneath the airfoil, a positive pressure results, particularly at higher angles of attack. But there is another aspect to this airflow that must be considered. At a point close to the leading edge, the airflow is virtually stopped, stagnation point, and then gradually increases speed. At some point near the trailing edge, it again reaches a velocity equal to that on the upper surface. In conformance with Bernoulli's principle, where the airflow was slowed beneath the airfoil, a positive upward pressure was created, i.e., as the fluid speed decreases, the pressure must increase. Since the pressure differential between the upper and lower surfaces of the airfoil increases, total lift increases. Both Bernoulli's principle and Newton's laws are in operation whenever lift is being generated by an airfoil. Pressure distribution. From experiments conducted on the wind tunnel models and on full-size airplanes, it has been determined that as airflow along the surface of a wing at different angles of attack, there are regions along this surface where the pressure is negative or less than atmospheric, and regions where the pressure is positive or greater than atmospheric. This negative pressure on the upper surface creates a relatively large force on the wing than is caused by the positive pressure resulting from the air striking the lower wing surface. Figure 3-8 shows the pressure distribution along an airfoil at 3 different angles of attack. The average of the pressure variation for any given angle of attack is referred to as the center of pressure, CP. Aerodynamic force acts through the center of pressure. At high angles of attack, the CP moves forward, while at low angles of attack, the CP moves aft. In the design of wing structure, the CP travel is very important, since it affects the position of the air loads imposed on the wing structure in both low and high angles of attack condition. In airplanes, aerodynamic balance and controllability are governed by changes in the CP, center of pressure. So low angle of attack, normal angle of attack, and high angle of attack, plus 10 degrees. It's producing lift, but you're slowing down a lot. Alright, moving on. That was page 3-9. I'm going to go to 310. Airfoil behavior. Although specific examples can be cited in which each of the principles predict and contribute to the formation of lift, lift is a complex subject. The production of lift is much more complex than a simple differential pressure between upper and lower airfoil surfaces. In fact, many lifting airfoils do not have an upper surface longer than the bottom, as in the case of symmetrical airfoils. These are seen in high-speed aircraft having symmetrical wings or on symmetrical rotor blades for many helicopters whose upper and lower surfaces are identical. In both examples, the relationship of the airfoil with the oncoming airstream angle is all that is different. A paper airplane, which is simply a flat plane, has a bottom and a top exactly the same shape and length. Yet these airfoils do produce lift, and flow turning is partly or fully responsible for creating lift. As an airfoil moves through air, the airfoil is inclined against the airflow, producing a different flow caused by the airfoil's relationship to the oncoming air. Think of a hand being placed outside the car window at high speeds. If the hand is inclined in one direction or another, the hand will move upward or downward. This is caused by deflection, which in turn causes the air to turn about the object within the airstream. As a result of this change, the velocity about the object changes in both magnitude and direction, in turn resulting in a measurable velocity, force, and direction. Third dimension. To this point, the discussion has centered on the flow across the upper and lower surfaces of an airflow. While most of the lift is produced by these two dimensions, a third dimension, the tip of the airfoil, also has an aerodynamic effect. The high pressure area on the bottom of the airfoil pushes around the tip of the low pressure area on the top. This action creates a rotating flow called a tip vortex. The vortex flows behind the airfoil, creating a downwash that extends back to the trailing edge of the airfoil. This downwash results in an overall reduction in lift for the affected portion of the airfoil. Manufacturers have developed different methods to counteract this action. Winglets can be added to the tip of an airfoil to reduce this flow. The winglets act as a dam, preventing the vortex from forming. Winglets can be on the top or bottom of the airfoil. Another method of countering the flow is to taper the airfoil tip, reducing the pressure differential and smoothing the airflow around the tip. Let's see, there's that third dimension. Vortices. Chapter summary. Modern general aviation aircraft have what may be considered high performance characteristics. Therefore, it is increasingly necessary that pilots appreciate and understand the principles upon which the art of flying is based. For additional information on the principles discussed in this chapter, visit the National Aeronautics and Space Administration, NASA. Beginner's Guide to Aerodynamics at http://www.grc.nasa.gov/K-12/airplane/index.html. That's nuts, man. Alright, good. So that was chapter 3. Chapter 3. See you later.